recorded that lecture. So anyway, it is section 12.1. I'm going to pull up the slides that I'm giving to my online class for 12.1. Yeah, I'm going to have to wear that on it. But I won't spend much time in them. You'll be expected to look at these on your own. But I want to go through a few of them. So when we have a scenario where we have two quantitative variables, so an x variable and a y variable, both being quantitative, none of them categorical, and we're interested in, is there a relationship between those variables? First thing you want to do is produce a scatter plot. Now you learned how to do that in algebra class, right? You got an x-axis and a y-axis, and each point on the plot represents an individual, a person or a subject, whatever it is that you're measuring, right? So we have what we refer to as an explanatory variable. You can remember that it's x for explanatory. So the x variable is explanatory, and the y variable is what responds to that. So you'll also hear it said the x variable is the independent variable, and the y variable is the dependent variable. It depends on x. Right? Can you think of two quantitative variables that would have some kind of a correlation, a relationship?
Height and gender.
He said height and gender, and that is true, but gender is not quantitative. I want two quantitative variables.
Age and height.
What?
Age and height.
Age and height, as long as it's before the age of 18 or so, then certainly there'd be, as they get older, they get taller. But after 18, they stop growing, so then that correlation stops, right? How about this one? The number of hours that you spend studying for this test on Friday, and your grade on that test. You'd expect as one number goes up, the other one will go up. If that occurs, that's what we call a positive relationship. So here, this is out of the book. This is kind of interesting, I thought. This is a sample of NFL quarterbacks. And so here's the name of some of the quarterbacks and their number of passing TDs that they've had, and then their salary, and then their quarterback rating, right? Now, if you're a quarterback in the NFL, would you expect there to be a relationship between number of TDs, passing TDs, and salary? Yeah, you kind of expect that the ones that can throw more touchdowns ought to be paid higher.
Wouldn't salary be determined before the season?
Well, that's one thing they don't really talk about. They don't really tell us what year this is, but there's passing touchdowns and base salary. Do you see a relationship? If there is one, it's negative. What does a negative relationship mean?
There's like an opposite correlation.
Yeah, it means it goes down as the other one goes up. Like the number of hours you spend in the bar this week and your score on the test Friday. As one goes up, the other is going to come down, right? So this is a little surprising, but I think you hit the nail on the head. You can think of a lot of reasons why this might occur, but salary generally is determined before the season starts, right? So I don't know, I didn't read it that carefully, but if this is number of touchdowns the year before and the salary this year, or how it's working here. But can you think of other factors that might go into the salary that have, something that don't have anything to do with number of touchdowns?
Age.
Well, there's also salary caps. Each team has a certain
Okay.
amount. So like Tom Brady has less money to be on the Patriots, even though he would get more in that team, but he takes the less pay to be on that team.
Okay. So what team you're on is another explanatory variable. It could explain some of the variation in salary because of what room they have in their salary cap and all that kind of stuff. Right? Anything else? Yeah.
Technically, actually win. Because you could score more touchdowns overall, but not necessarily win.
Yeah, you could not have that many passing touchdowns, but still be winning a lot of games because you're, successful at the other parts of the game, right? What about the quality of the receivers on the team? It might not be the quarterback's fault, right, that they're not catching these passes. So there's a lot of other variables that could go into it, right? So one of the things that we're going to learn is the correlation coefficient, but also this concept of what percent of the variability in the y variable is explained by this x variable. The percent that is not explained by that one is presumably explained by some other variables or possibly just random noise. Right? So we need to learn how to separate those things out. So the correlation coefficient, let me get to this. When I say the correlation, it's short for Pearson correlation coefficient. And I would actually add a word in there, Pearson linear correlation coefficient. And I want to stress linear because it only addresses scatter plots that have the shape of a basic line. If there's some other shape, a curve, then this isn't going to do you any good, right? So R, lowercase r, is the correlation coefficient. And I'll put in parentheses linear. It's the linear correlation coefficient. Now it says here that the correlation coefficient varies between -1 and 1. So what does a correlation of 1 mean?
It's a straight line.
Okay? A correlation of 1 means that the points fall exactly on a line. It's called perfect correlation. Right? And it's positive, so the line is sloping up to the right. Okay? If it's a negative correlation, the line is sloping down. But if it's -1, that's perfect negative correlation. Understand? So what would 0 correlation look like?
There's no trend.
There's either no trend at all, or somebody said, flat line, meaning horizontal line, right? You could have lines that fall, points that fall exactly on a horizontal line. I can't draw them that perfectly, but exactly on a horizontal line, that looks like perfect correlation, but since the slope is 0, it's saying y does not change as x changes. Y does not, or x does not help me predict y. So there's no correlation. The salary is staying the same no matter how many touchdowns we score. Okay, now, the formula for correlation. There. Got it? I'm showing this to try to scare you into dropping the class. No, not at all. This thing is, it's a horrible looking formula. I'm not going to make you use this formula point by point by hand and figure it out. Our calculator will compute this automatically. I added to their slide here that this is a computational form of an equivalent expression for correlation, which I'll show you on the next slide. This is for computational purposes. This is old-fashioned. We don't do this anymore because we got these fancy calculators. We got Microsoft Excel. We got software. So we don't have to know, the computational that makes it easier to do with a handheld calculator. But here's the one I want you to know. And again, I won't make you use this formula, but I may ask you questions about it to make sure that you understand it. You can show, it's a lot of algebra, but you can show that this equation is algebraically equivalent to the one on the previous slide. So what am I looking at here? Well, what is this? Summation. This big Greek sigma is summation, right? So I'm summing up the product of two things. Now look at each of those things. Look only at this. What does that look like? Does that look familiar? It's a z-score. Very good. I've mentioned there's a test Friday, right? Z-scores will be on that test. This is a z-score for the x variable. This is a z-score for the y variable. So you take each person, you figure out their z-score for x, their z-score for y, and you multiply the two things together. Then you sum those up across all of the subjects. So here's how it works. Let's do a scatter plot. Let me, before I do it, I want to use some data from your class survey. Oh, I got to go to the next slide set. Here. This is data on shoe size as the x variable and height as the y variable. Now when you look at that, do what I call the eyeball test. You're just looking at it and deciding, is there some kind of a relationship here?
Positive.
Looks like a positive linear relationship. It follows a line. Right? So as long as you see a linear relationship that's at least fairly strong, then it's okay to use linear regression and correlation to analyze the data. Right? So what I did here, so that I had a small enough number of points to enter into our calculators as practice here in a minute, is I took one woman. These are all females. I took one woman with each shoe size that was turned in. So there was a shoe size starting at 5, size 5 shoe, and every half size up until I think we got to 10, and then it started to jump. There was no 10.5, there was an 11, there was a 12, and there was a 13. Okay? So there's 14 data points there. So I'm gonna sort of copy that thing down here, but I'm not going to worry too much about how good it looks. Looks kind of like that, right? Now, if I ignore the y variable, which is height, and I look only at shoe size, think about dropping all of these points straight down onto this axis. Where would the mean of those points be? It's not a trick question. Okay, about 9. What I was looking for was in the middle, right? Which would be about 9, right? So about right there, if I drop a line, that would be the average of the x variable, which the x variable is shoe size. So instead of a black dotted line, because I'm going to get confused with my dots, I'm just going to draw a red line through that. So everybody that's over here left of that red line has a smaller than average shoe size. Everybody that's to the right of that red line has a bigger than average shoe size. Right? Now do the same thing with height. Reflect all of these points over to the y-axis, and then what would the average be? About in the middle. See, now you're catching on. About in the middle. So that point right there is what you don't have to know this word, but that point is called the centroid. Basically the center of the cloud of points. And we're going to talk in a minute about the line of best fit. The line of best fit must go through x bar, y bar. So if I draw a red horizontal line through that point, that's not real horizontal. How about that? Everyone above that line is above average height. Everyone below that line is below the average height. Right? Now go back to that formula for regression, or for correlation. Let's pick a point. Let's pick this point right there. Right? Mentally, give me the z-score for that person's shoe size. And positive or negative is good enough at this point. Would this be a negative or a positive z-score for shoe size?
Negative.
Be negative because they're below their mean, right? What about their z-score for height? A negative. So in this square, I'm going to get a negative times a negative. If you multiply a negative and a negative, you get a positive. Now pick one up here.
Positive.
Both would be positive. Be positive, positive, multiply together, you get positive. Okay, oh, but look at this lady. I started to say this guy. Look at this lady.
Positive, negative.
That one is a positive for shoe size, very small, but positive for shoe size, and negative for height. So you're going to get a negative value when you multiply together. And same thing up here. I didn't have any points, so let me add one. If you have a point up in this square, this quadrant, you're going to have a negative times a positive, which is going to be a negative. So if you have points that are mostly in this quadrant and this quadrant, you get mostly positives when you sum these products up. Right? If you have mostly points coming down through here, guess what happens? Mostly negatives. Right? What happens if I stand at the back of the room and I shoot my shotgun? Boom! So I get points pretty evenly dispersed between the four squares. Now I get about an equal number of negatives and an equal number of positives. Guess what happens when I sum them up? They sum to 0. So 0 correlation indicates they're all over the place. Right? It can mean a couple other things too, which we'll come back to. It can mean this. Right? What if I did the same thing and I say, okay, let's mark the centroid and let's draw the lines. Right? Now all of the points fall right on the line, so they all have 0 z-score for their y, so it adds up to 0. What if I have, let's do this. What if I have this? So I got a real nice, strong relationship between them, but it's not linear. What's going to happen? These are going to be positives. These are going to be negatives, and they pretty well match in terms of their z's, just positive and negative. So these are going to add out to 0. What about these and these? They're going to add out to 0. I'm going to get 0 correlation again. So 0 correlation does not necessarily mean no relationship at all. It means no linear relationship. Right? So that's an important part of this Pearson correlation coefficient, is that it's a linear correlation. If you have a curved relationship, it may still be very strong, but you need a different statistic to measure that. And lucky for you, we don't have to do that in intro stats. But they're out there. Okay? Well, let's go back to the shoe size and height one. And let's talk about, actually before I do that, let's compute, there's the data. These are the 14 points that are being graphed on that slide. All right? So let's compute the correlation coefficient. And I already told you, you don't have to use the formula, you get to use your calculator to do this. So, get your calculators out. And the first thing I want you to do is I want you to put the shoe size into L1. And then put the heights into L2. and you have to make sure that they match up. So the first row for L1 has to be paired with the 57th. You can't put them in reverse order, you screw it all up. Now it works. Okay, so everybody got the data in? All right. Now, let me pull up the instructions that they give us. This is in your book, but I will warn you, I modify from what the book tells you to do a little bit. There are other places in the calculator to get the linear correlation and the line of best fit. But they don't always work for you. You have to have your options set the right way, and it gets people confused and they start crying during tests. Right? So do this, it always works. Right? So push, after you've got the data entered, push the stat button, then go over to test. And I think I left the S off of the word test. It has an S on it, right? Okay. So go over to test in your calculator, and then go down, and it's way down, near the bottom. Go to Lin Reg T-test. Any guess what Lin Reg is short for?
Linear regression.
Linear regression. The T-test part, in the book, they'll talk a lot about test to see if the correlation is statistically significant. And that's what that test is all about. But we haven't learned hypothesis testing yet, so we'll come back to that after we learn that. All right? So when you do it, you should get a screen that looks like this. So X list, if it's not already there, set it as L1. And set Y list as L2. Those should be the default. So if you've never changed them, that's what they're going to be. This needs to be a 1. Where it says freq for frequency, if it's not a 1, you have to make it a 1. Right? This is when you have another list that tells you the frequency of these points, and we don't have that problem. Everybody good? Ignore all this. This is about the hypothesis testing of the correlation. Go down and hit calculate. And when you do that, you should get 2 pages of output. And you'll arrow down to get to the second page. And all the way to the bottom of the second page is the correlation coefficient. So in this case, R is 0.903. What did we say the bounds for R were? What's the biggest it can be? 1. And 1 means perfect, right? That they fall exactly on a line. Well, these points don't fall exactly on a line, but they're pretty close. It's easy to see the line, so you know it's going to be pretty strong correlation, right? The more spread out around the line they get, the weaker and weaker it gets. Okay? Now, right above that is R squared. And R squared, do you remember what that's called? Good. Coefficient of determination. It's not measuring how determined you are to get through stats class. It's measuring how strong or how much variability in the Y variable is explained by this X variable. Remember I was saying that a minute ago about passing? Well, by knowing somebody's shoe size, I can explain a lot about how tall they are. In fact, 81% of the variability in height I can explain just by knowing their shoe size. That means there's 19% that I cannot explain with shoe size. So what would explain that?
Genes.
Genes, genetics, sure. Anything else? Random chance is an okay answer. Right? Just, there's things that we don't know why this brother is taller than this brother. They got the same genetics, you know. Maybe one ate better. Maybe, who knows? That's unexplained variability. We have 81% explained variability, and we have 19% unexplained by this data. Got it? Okay? So that's how you'll use your calculator to get linear correlation coefficient.
How many variables? How many
numerals line do you want us to go on this?
How many decimal places? That's a good question. I think online they usually tell you to use 4. I stopped at 3 decimal places, but if I went to 4, it'd be 31, 9031. So do pay attention to what they tell you on the test. I usually don't remember to say how many, but 3 or 4 for correlation is enough. So we'll go with that. Now let's look at what else is given to us on this output. If I come back to this mess, I'm going to clean this up. So my data points were something like that. And we have this centroid that we know the line must go through. Right? The line of best fit goes through that centroid and through the middle of the rest of the cloud of points. What? Line of best fit. Define best.
It's best representation of the data.
Okay.
The averaging.
But how do you know that that line that I just drew is better than that line?
Because it has equal number of points on either side of the line.
Okay, good. Now you're kind of getting at it. He said equal number of points on one side of the line as the other. But it actually doesn't have to be equal number of points, but equal magnitude of the prediction errors. Prediction error. Oh, well, looky here. Let's say that, let me get the red line out of there. Let's say that this black line is my line of best fit. So for this person right there, the line would predict they would be that tall. So that we call Y with a hat over it. Y hat. And a hat in statistics means estimated value or predicted value of. Right? So the predicted value of Y, which is height, is that red point. But this person was shorter than you would predict based on their shoe size. That difference between them is called a residual or prediction error. So the line of best fit minimizes those prediction errors. Now, just like when we computed standard deviation it seems like a long time ago, doesn't it? Remember we had problems with negative deviations and positive deviations, and when we summed them up, they summed to 0? Same thing will happen with residuals. Some are below the line, so they'll be negative. Some are above the line, so they'll be positive. If I just sum them, they sum to 0. As long as I go through that point, they will always sum to 0. So what do we do to get rid of negatives? What do we do with standard deviation? What? We squared them. So if I square these prediction errors, then I sum them up, now I got something I can minimize. I can find the line that will minimize the sum of the squared residuals. So we call it the least squares line for short. Least meaning least squares meaning squared residuals. Least squares line. And that gives us what we'll refer to as the regression equation. Now in your calculator, it tells us right here that y equal a plus bx. And then they tell us what a is, and they tell us what b is. Right? That's different notation than what they have in the book, but it means the same thing. Notation is one of the things that scares a lot of people away from studying statistics, because I can't remember all the Greek letters and the symbols and all that crap. Right? But just understand conceptually what it's doing, and it's not so bad. So calculator uses y equal a plus bx. The book uses y with a hat over it. And technically, there should be a hat over it. I think it's just hard for the resolution of the calculator to put hats on things. But they use b sub 0 plus b sub 1x. This is more typical notation from the field of statistics than the a plus bx. But when they wrote the calculator, they were trying to keep it simple. But just know that those things are interchangeable. The important thing is, what are those numbers doing? If I tell you this is the equation of a line, you should go, ooh, I remember this. College algebra. Equation of a line. What's that form of the equation of a line called? The slope-intercept form of a line. Oh, that was other notation. That was mx plus b. Right? Don't write that down. You got enough. Which one is slope and which is intercept? M is the slope. So which one's the slope over here? B, because it's the one multiplied by x. Don't get fooled by what you learned out of the B was the intercept and I'm not changing. Right? Now they use different notation. But just know that whatever's being multiplied by x, that's the slope of the line. The other one is called the intercept. So this one that the book uses, B1 is the slope, B0 is the intercept. Okay? So let's write down the equation, and then let's get the interpretation of the slope and intercept. So we have A is 51.348 if I round to 3 places, plus the slope, which the calculator calls B, is 1.680 if I round to 3 decimal places, times x. So this is known as the regression equation, the line of best fit. And when I plot that line of best fit through the data, it looks like that. Okay? Everybody get that on their calculator? All right, so let's talk about interpretation. 51.348, the B0. What is that? What did you say?
That's where it intersects the y-axis.
Okay, it's where the line would cross the y-axis. Well, the y-axis, is it even on this graph? Well, it's not in the right spot because this stops at 5. So the y-axis, I thought that was my thing, I'm going nuts. The y-axis, if this is 6, this is 5, would be about 4, 3, 2, 1. It'd be about over here. If I extend that line down to here, it would be at a height of 51.348.
You have size 0 shoes.
Exactly. And that point, he's kind of making a joke, and I was going to beat me to it, but size 0 shoes, does that make sense? No, but that's what that number means. If somebody had size 0 shoe, we would predict them to be 51.348 inches tall. It does not always make sense to extrapolate back to when x is a 0. Sometimes it does, sometimes it doesn't. If your x variable can't go to 0, don't worry about it. You don't have to use that number other than as a starting point for the line to take off. The one that's really important is this one, 1.68. So what is that? 1.68 what? I will, not if, but will have a question on the test that says, interpret that number. Okay? See, that's the way my brain works. He's drawing stuff. You go up. This is known as, oh, by the way, on the test, when I say, give the interpretation of the 1.68, and you say, it's the slope, I'll say, that is correct, minus 3. I want you to interpret in the context of the problem. Talk about shoe sizes and height. What? What does that mean?
Where we have a susha. shoe size go up?
Not a half a shoe size. For every 1 unit change in the X variable. We have half shoe sizes, but look what happens. If I start here at, say, size 6 shoe, there's my line, and it looks to be almost 61 inches or 62 inches tall, right? If I go 1 more unit over here to 7, it's up, looks like about that point is almost exactly on the line, which is about 1.5 inches higher. Hey, it's 1.68 inches higher. That's what that number means, right? So no matter how fine your grid is, it's always a 1 unit change in X. It's rise over run, just like you learned in algebra, right? It's also known as a rate of change. How fast is Y changing as X changes? All right? So this is female data. Let's see. Does anybody in here have a size 7 shoe? Females? Size 7? I'm going to use her because you look too tall. How tall are you?
I'm like 5'4".
5'4". Okay. And who has a size 8 shoe? Okay. She beat you on her hand, but I'll ask you. How tall are you?
5'7".
5'7". So you're 5'4". You're 5'7". That's a 3-inch difference. The line would predict a 1.68 inch difference. And how tall are you? 5'4". That's why I didn't want to use you, because you look about the same height. You get good when you do this for 15 years of picking the people out that make your lecture work. We didn't quite work. We went 3 instead of... But you get the idea? Right? So the regression equation is not going to be perfect. There's prediction error. But on average, we predict that somebody whose shoe is 1 size bigger than another person, should be 1.68 inches taller on average. Got it? That's linear regression. Okay? Now, what I want you to do next is predict the height of a woman with a size 10 shoe. Predict the height of, I should have said, of a woman with size 10 shoe. You do it on your paper, and I'm going to come around and look at it. Okay, good. That's right. Okay, you're not there yet, but you're getting it. You're doing the right thing.
I'm not sure where to start.
Okay, here's a hint. I purposely didn't say how to do this, did I? But since we're using the regression equation to make predictions, use that equation, the y-hat equation. See if you can figure out how to do that. You got an answer? Yep, that's right. Good, same number. Okay, good. You got a number? Yep. Perfect. You know,
I have my calculator right now.
well, you can do that in your head, right?
Yeah,
I'm just kidding. I couldn't do it in my head. You got a number?
Well, I did, but I don't think it was right, so
What was it?
it was like negative 24.
Yeah, that's not right. Which is exactly what I want you to do on a test. If you get a number and go, oh, that can't be right, then go looking for your error.
I don't like that camera is like on me now. 'Cause you're like,
Good, that's right. Yep. 68.148. Is everybody getting that? So here's how to do it up on the screen.
your camera's stuck.
Oh, I broke it. I can't find the right page. There it is. You want to plug in. I must have walked in a circle around it. It probably can't unwind itself. So you're just going to take the number 10 and plug it in where x is. So on the test, when I say find the regression equation, boom, you're going to write it down. And then I'll say use your regression equation to predict whatever the y variable is from an x of this value. And I'll give you a number. You're just going to plug that number into the equation. And that's your predicted value. Right? Now, what if I ask, this is actually not taught in this book until section 12.3, but I'm going to hold you responsible for knowing what we mean by residual or prediction error. So if I say, well, what's the prediction error for the one that had a size 10 shoe? Well, you'd have to go back to the data. So let's go back to the table that had all the data. What's the actual value for a woman with a size 10 shoe? 68 inches. So residuals are y minus y hat. All right, that's residual. So that's 68 minus 68.148. And that's, I can do that in my head. That's why I picked this one. Negative 0.148. Now that's inches. Everything's in units of inches, whatever your y variable is, right? So the residual is negative 0.148 inches. So that's only a little more than a tenth of an inch, right, that we're off. But go back to the picture and you'll see that that point fell really close to what? Where's the size 10 shoe? Here's 10. It's that one. That point fell really close to the line. So it has a very small residual. But it is slightly below the line, so it's negative. What about this one? What would the residual be there? Just guess by looking at the picture. It'd definitely be positive. About how many inches? About 2. I'd say about 2. Because if you look on the scale here, there's 2 inches. A little more than 2 inches. So you'd have a residual of 2.1 or something like that. All right? Any questions? All right. I think I've already done it, but out on D2L there will be a Exam 1 review document of some title like that. So get that, print it out, and have it all filled out for class on Wednesday. And that's what we're going to go through on Wednesday. If you have ones you don't know how to work, then come to class prepared to ask. If anybody asks any questions, we're done. So if you want to learn something, you'll be prepared with some questions. We'll see you then.